This is going to be my second attempt at my speaking skills talk, and this is again going to be on new results for exponentially improved dimension reduction in L1. This is going to be appearing in COLT 2021 in about a month or so, and this is based on joint work with E. Lee and David Woodruff. Okay, so the main topic of this work is going to be on dimension reduction, which is essentially a set of techniques which allow one to reduce the dimensionality of data sets while approximately preserving their properties of interest. And to specify this a bit more precisely mathematically, we're going to think of having an input of data in n dimensions, where n is very large. And what we want to do is we want to pretend like this data set is in a much smaller R many dimensions, where R is much smaller than n. And in order to do this, what we want is a map F, which maps from n dimensions down to R dimensions, such that f of x will approximate x. So this is kind of the goal. And the general motivation for this kind of dimension reduction technique in general is this phenomenon known as the recursive dimensionality. So this is an observation common in both theory and practice, that when we work with high dimensional spaces, then these are often exponentially harder to work with in terms of space resources, time resources, and all kinds of other things. So whenever we're able to reduce the dimensionality of a data set, this leads to really large savings. And for the purposes of this talk, we're going to focus on a particular form of dimension reduction known as sketching. So sketching in one line is linear oblivious dimension reduction. So it's a special type of dimension reduction where linearity means that we want our map F to be of the form f of x is equal to s times x for a random R by n matrix S. And by oblivious, I mean that this randomness for S is independent of the data set that we're working with. So this is the particular form of dimension reduction we're going to be focusing on today. And to illustrate this in pictures, we basically want to choose this random matrix S, which is R by n. And notice that R here is very small compared to n. And we want the property that if we have a fixed vector x in n dimensions, then this product S times x is well approximates the original vector x. And the notion of approximates here is going to be that if I look at the norm of this vector, so if I look at the norm of Sx, then I want this to be at most 1 plus epsilon times the norm of x, where here epsilon is like a small number, say 0.1. And I also want this to be at least 1 minus epsilon times the norm of x. So I'll often write this as the norm of Sx equal to 1 plus or minus epsilon times the norm of x. And as I mentioned earlier, we often want to take this matrix S to be random. So I want this guarantee with probability at least 99%. So this is broadly the setting that we're going to be working in. And here again, R is the main resource of interest, where we want R to be as small as possible while still preserving this guarantee that the norm of Sx is approximately the norm of x. Now, why would we restrict ourselves to this like linear oblivious dimension reduction? Well, it turns out that this is useful for many purposes. For example, it's very efficient to estimate pairwise distances when we have this restriction for linearity and obliviousness. So why is that? So suppose that we want to estimate the distance between x and y, which is the norm of x minus y in norm spaces. And by the approximation property of this sketch, we have that this is approximately equal to the norm of S applied to the vector x minus y. And now by linearity, this is just the norm of the sketch Sx minus the norm Sy. So what this is telling us is that using the linearity of the sketch, it just suffices to sketch every vector in order to get pairwise distance estimates between the vectors. Another setting where the sketching is very useful is in streaming environments, where we think of our underlying vector x as undergoing dynamic updates. So in this setting, it turns out that this linearity allows us to efficiently update our sketches. So what this means is that if I want an updated vector x plus delta and then sketch it down, well then by linearity, s applied to the new vector x plus delta is simply just sx plus s delta. So all I do to update the sketch is sketch my update delta and then add it to my original sketch SX. And a third setting where this is useful is in distributed settings, where I think of X and Y as two vectors that belong on different servers. And in this setting, it turns out that sketches allow for efficient aggregation. So what I mean is if I want to sketch the aggregate vector X plus Y, then what I can do using the linearity is to say that, well, this is just equal to SX plus SY. So if I have access to the sketches XY and SX and SY, then it just suffices to aggregate these two sketches, which is only in R dimensions, rather than the n-dimensional original vectors X and Y. So this is why we would essentially want to consider the sketching model. And I first want to get into prior work about these dimensionality reduction results in the sketching. So the celebrated classical result here is by Johnson and Lindenstrass in 1984, which essentially gives dimension reduction results for L2. And here, what Johnson Lindenstrass says is that we can just take S to be an R by N matrix of just all ID Gaussian variables. And in this setting, if we have a fixed vector X, then it turns out that we can take our target dimension R, so this is the number of rows in our sketching matrix, to be only 1 over epsilon squared in order to get the guarantee that we discussed previously, where the 2 norm of the sketch SX is within a 1 plus or minus epsilon factor of the 2 norm of X. But the results here go further. So suppose that we want to preserve the norms of m vectors simultaneously. And in this case, Johnson and Lindenstrass show that we only need to take our target dimension R to be only a log m factor more than the single vector case. And what happens then is we still get the same guarantee that the 2 norm of Sx is within a 1 plus or minus epsilon factor of the 2 norm of X, but this time simultaneously for all m vectors in the set big X. And finally, suppose that we actually have a matrix A, which is n by d. And suppose that we want to simultaneously have this norm preservation guarantee for all vectors in the column span of A. In this case, Johnson and Lindenstrass show that by taking R to be only 1 over epsilon squared times d, we're able to get this guarantee of norm preservation for all vectors in the subspace. And this is a powerful guarantee known as subspace embedding. And we'll be talking about this guarantee a bit more as well. So to summarize, Johnson and Lindenstrass results imply that if we want to embed one vector, then we only need a target dimension of 1 over epsilon squared. And for m vectors, we need 1 over epsilon squared times log m. And finally, for a d-dimensional subspace, we need 1 over epsilon squared times d main dimensions. And these results have many applications and are very useful, both in theory and practice. So for example, as mentioned earlier, this primitive is very useful for streaming algorithms. And actually, for linear regression as well, it may seem sort of unrelated, but this last guarantee for the subspace embedding allows one to treat a large matrix that you want to do linear regression on as a much smaller matrix. There are more applications such as low rank approximation, clustering, and nearest neighbors, but I won't be getting into these for this talk. So one can ask, what kind of results can we say for L1? So to remind you, the L1 norm of vector x is just the sum of the absolute values of its coordinates, also known as the Manhattan distance. And the reason why we might want to consider L1 instead of L2 is that the L1 norm is considered as much more robust than L2. That is, it's much more insensitive to outliers in various applications. So for example, the linear regression example that I discussed earlier for L2 transforms into the least absolute deviations linear regression problem when we replace the L2 norm with the L1 norm. And in picture, I'll show you what kind of outlier insensitivity this will demonstrate. So if we have this data set where we have this like diagonal set of points, which roughly looks like it lies in a line, but we have these outliers, then an L2 linear regression or least squares linear regression will actually not succeed in finding this line that we want the linear regression to go through. However, an L1 solution will actually be much more intuitive and fit these lines, being insensitive to these other outliers that we don't want to consider. And so this difference can kind of be described as something like the difference between finding the mean of a point of a set of numbers and the median of a set of numbers, where it's a well-known fact that the median is much more sensitive or insensitive to outliers. And because of this property, it's known that the Manhattan distance is consistently more preferable than the Euclidean distance or the L2 distance for high dimensional data mining applications. So we're really interested in getting these dimension reduction results for L1 rather than L2. So what's known? So recall that for L2, Johnson-Lindenstrauss proved that if S is a matrix of ID Gaussian variables, then we get L2 dimension reduction. So can we do something similar for L1? So actually, Indic in 2006 proves that there is actually an analog of this result, where instead of taking a matrix of ID Gaussian variables, Indic considers a matrix of ID Cauchy variables. So Cauchy is another distribution, and in some sense, it's the L1 analog of Gaussian variables. And he indeed shows that L1 dimension reduction is possible, but there's a caveat here, in that the success probability is very low. So we wanted 99% success, as I mentioned earlier, but Indic's result only gets an epsilon probability of success. This line of thought was further pursued by Wing and Woodruff in 2019, where they also consider a matrix of ID Cauchy variables, which leads to L1 dimension reduction. And this time, the results have sufficiently high probability, so we can, for example, indeed get 99% success probability. But the problem is that their bounds on the target dimension R are actually doubly exponential, which is very undesirable. So let's take a look at these results a bit more. So I'm just going to be comparing the upper bounds and lower bounds obtained by Wing and Woodruff against the L2 results for Johnson-Lindenstrauss. So for one vector, the upper bound obtained by Wing and Woodruff using the Cauchy variables is actually going to be doubly exponential in 1 over epsilon squared. So this is definitely undesirable. And the corresponding results for M vectors and D-dimensional subspaces are similarly doubly exponential, where essentially the bounds are whatever you get for Johnson-Lindenstrauss for L2, but you take the double exponential. And furthermore, they also have lower bounds or impossibility results, saying that if I want to preserve the L1 norms of M many vectors, then we actually can't get lower than a target dimension of 2 to the square root M. So here, this singly exponential dependence on M is actually tight. And this immediately implies a lower bound on embedding D-dimensional subspaces as well, since if I want to embed a D-dimensional subspace, then in particular, I must be able to embed D many vectors. So these are the known bounds so far. And we can notice that there's a an exponential gap between the known bounds for D-dimensional subspaces. So the question we ask is, can this gap be closed or not? And our result answers this in the affirmative. So for the result for one vector, we're actually able to improve this upper bound to only singly exponential in 1 over epsilon. And these results carry over for our other two results as well. So for M vectors, the upper bound is now 2 to the M over epsilon. And for D-dimensional subspaces, it's 2 to the D over epsilon. So to interpret our results a bit more, so what we've done is we've lowered the dependence on D and 1 over epsilon from doubly exponential down to singly exponential compared to the previous known results. And the dependence on D here is tight up to polynomial factors in the exponent by a given lower bound from Wing and Woodruff from before. And finally, our results say something very interesting about the difference between the characteristics of L1 and L2. So if we take a look at the last two rows of our results, we'll see that the bound for M vectors and D-dimensional subspaces is essentially the same. So what this says is that L1 really doesn't care whether we embed D many vectors or the entire span of these D vectors. So what's easy, so for L1, like it's as easy as preserving D vectors as it is to preserve an entire subspace. But on the other hand, for L2, there's actually an exponential difference. So for M vectors, we only need log M times 1 over epsilon squared, but for a whole D-dimensional subspace, we actually require a dependence on linear in D. So these are our results, and I think now is a good time to take any questions if you have any.
Sorry, I missed what you said. So the lower bounds for what values of epsilon are you talking about?
For this is a fixed epsilon for the lower bound.
So I should think of it like 1% or something.
Sure, yeah, exactly.
Okay. Fair enough. Okay, thank you.
Yeah.
Are there any lower bounds in terms of epsilon?
So for epsilon, there are no known lower bounds. So this is open, but I suspect that the dependence here of singly exponential on epsilon is also correct. And I can talk a little bit about why I would believe that.
Yeah.
But that'll come up later once I go over our techniques. Okay. Are there any other questions so far? Okay, great. So for the rest of the talk, I'll be talking about the techniques that are used to obtain these results. So first, I'm going to be going over the high-level ideas used for our results. The first one being for embedding one vector and improving the dependence on epsilon, and the second for embedding a whole subspace. And then what I'll do is I'll go into more detail about the proof for embedding one vector. So in order to improve the dependence on one vector on epsilon, we actually switch our approach. And instead of going through the Cauchy variables, we actually switch to using a different starting point, which is known as msketch. And this is worked by Clarkson and Woodruff in 2015. And instead of using these Cauchy variables, we actually use a different set of techniques, which are well known in the streaming literature, based on sampling and hashing. And I'll go into more detail about these later. And it turns out that these techniques are only able to achieve an O of 1 distortion. And this is a limitation of their work. However, we're able to put a new spin on this technique by randomizing the sampling rates of the sampling process themselves. And this is going to allow us to achieve a 1 plus epsilon distortion with only a singly exponential dependence on 1 over epsilon. So this is the high-level idea of our improvements for embedding one vector. And in order to embed a whole subspace and improve the dependence on D, so the classic technique for L2 turns out to not work. So in the L2 case, the classic technique is to use a net argument, which essentially means that we discretize the unit sphere with essentially 1 over epsilon to the D many vectors. And then we apply the previous one vector embedding result to every single vector in the net. And then by union bound, this implies the type bound of 1 over epsilon squared times D for L2. However, in our case, it's going to turn out that this technique provably does not work, and it still leads to doubly exponential bounds on D. So instead, we need a different approach. And our idea here is going to be to use L1 leverage scores, which is a notion which was introduced by Clarkson, Drinius, Magnon Ismail, Mahoney, Meng, and Woodruff in 2013. And so I'm going to briefly illustrate this idea. So recall that we had a matrix A, which is an n by D matrix, which specified our D-dimensional subspace. And associated with this matrix is a vector known as the L1 leverage score. And so this is an L1 unit vector that has the following property, that this vector lambda, the L1 leverage scores, approximates the coordinates of every single vector in the column space up to a factor of D. So for example, if I were to look at the first coordinate of this leverage score vector, and if this is of size 1 over D squared, then no vector in the column span can be of size at like more than 1 over D, say. So this gives us essentially one single good vector that leads to very good approximations for this entire subspace. And what we do is we show that if we, yes?
I didn't understand that at all. Could you repeat that, please?
Yeah. So essentially, the L1 leverage score vector gives us a single vector, which depends on this matrix A, such that if I look at this vector, the coordinates of this one vector simultaneously approximates the coordinates of every single vector in the column space up to a factor of D.
I guess I still don't understand. What does that mean? So you, for any matrix A,
yeah,
you have a single vector.
Yeah.
And so now you're trying to approximate the coordinates of the span of the columns of A?
Yeah. So
go on.
Yeah. So I'll take some column space vector AV and I normalize it so that it has L1 norm 1. And then after I do this normalization, I'll have the property that for any coordinate of this column span vector AV that's normalized, this coordinate cannot be more than a factor of d larger than the corresponding coordinate for this leverage score vector.
Ah, I see, I see. So it's a multiplicative approximation that depends on the number of columns.
Yeah, exactly.
Okay.
And so this is like it can't be larger by a factor of d and smaller by a factor of d as well. So it's
There's no guarantee on the lower side. It's only the upper side guarantee. But this is all we need for the purposes of our technique.
so lambda of a is no bigger than d times the corresponding coordinate of AV.
No, so any coordinate of AV is no more than d times larger than the coordinate of lambda.
Okay.
And lambda is a unit L1 vector.
Yeah.
Okay.
Lambda is a unit L1 vector.
Yes.
It makes sense. Okay.
Yeah. So
Okay.
okay. So is that clear to everyone?
Now it's much better. Thank you.
Okay. Yeah. No problem. So our technique is essentially going to be applying our one vector embedding results to the single L1 leverage score vector with an accuracy parameter epsilon, which is a d factor smaller. And this is essentially what's going to give us the result that we want. Okay, are there any other questions for this? Oh, and sorry, to get back to Samson's question about why I think there's an exponential dependence on epsilon. Here, we're able to show that applying a one vector embedding with a different epsilon parameter leads to efficient embeddings of a whole subspace. And this is a non-black box use of this technique. But essentially, like if we were able to black box this use of the one vector embedding, so if I can say that if I have any good one vector embedding, and if I can show that this embeds this one leverage score vector well, if it leads to good subspace embeddings, then this translates to a lower bound for epsilon as well. But this hasn't been formalized, and I don't know if this is true or not.
So Ty, at this point, are we supposed to understand why just embedding the leverage score vector implies something for the
no. So this last line, this is going to depend on a non-black box use of our one vector embedding. So, and I haven't even discussed that, so it'll be hard to understand. But this is just an overview of what we do for subspace embeddings.
Good, thank you.
And one more question. So, okay. So obviously lambda leverage scores are data dependent. Is your sketch oblivious, or you're not actually computing?
Right. Yeah. The sketch is still oblivious. So the use of the L1 leverage score is only for analysis.
I see. Okay.
Okay. Were there any other questions?
So I forget, the sketch is randomized and it's going to succeed with high probability.
Yeah, with constant probability, say 99%.
Okay. Okay.
Okay. Yeah. So the subspace embedding, like I have the guarantee for the entire subspace, but that happens with probability 99%. That's
Sure. Okay.
So just to check I actually don't know how this how you go from embedding the leverage score vector to embedding the subspace. But the naive thing, just to understand what I should understand from this slide, is that if you were able to embed, say, the leverage score vector, say with a 2 approximation, then you would get a D approximation to the subspace, just because the leverage score vector approximates everything up to a factor of D.
I think that would only hold on one side. Like I think you would show that you don't get an expansion, but I don't know if that leads to the lower bound. So like that the property that I don't shrink any vector.
Okay.
Okay. If there are no other questions, I think I'll move on.
Sure.
Okay. Okay, so far I gave the high-level ideas for embedding one vector in a subspace. And now the next thing I want to do is to go into this embedding of one vector in more detail. So this one. And in order to do that, I'm first going to introduce the M sketch by Clarkson and Woodruff, which gave the O of 1 distortion. And then I'll show how to modify this in order to get this 1 plus epsilon distortion. Okay, so the first step is M sketch, which we're looking for an O of 1 distortion from. And before we get into this, I'm going to simplify the inputs a little bit so that I'm going to have an easier time doing the analysis. So first, without loss of generality, I can assume that the entries of X have random signs. And this is just a simple observation. So if I have a sketch S that works for X that has random signs, then what I can do is I can multiply random signs myself and introduce this diagonal matrix of random signs. And then I can treat this diagonal matrix as part of my sketching matrix S instead of as part of the input. So this is why I can assume that X has random signs. And furthermore, I'm going to.
Whoa.
Oh, sorry.
What just happened? So you're assuming that the entries of X have random signs?
Yes. And this is simply because I can just multiply by my random signs myself. So I can treat the multiplication of the random signs as part of my sketch.
Okay. Okay.
So that's one simplifying step. And the other simplifying step is that I just want to assume that X is M sparse with random signs on its support. And this is also basically without a loss of generality, but it requires a simple proof, and I don't want to get into that for now. So what I mean by this is for my vector X, I want to choose a random set of M coordinates. And then I just want to assume that this X just has plus or minus ones on these random M coordinates that I choose. And note that I don't know what M is, and it has to work for all M simultaneously. But assuming like for some M, it's going to have this structure. And for some random support. So this is my assumption.
The port locations are also random apart from the signs being random?
Yeah, so I'm going to pretend like I just don't know what the supports are. They can be adversary, they can be random. I just don't know what it is.
They're not random, they're adversarial.
Sure, yeah. It turns out that it doesn't matter, but yeah.
So just to understand, maybe I misunderstood earlier. So basically what you're saying is that you can assume that the vectors that you want to sketch are plus, minus 1 or 0 coordinates. That's what you're saying, right?
Exactly, yeah.
Okay.
Okay, and we're going to parameterize by.
Wait, hold on. I think you can assume that the vectors are plus minus 1 coordinates, or that they have random signs.
Yeah, this also I misunderstood, but like the first line says that they are random signs themselves. So not that their signs are random, but they are random signs.
So that's an additional assumption. So I'm assuming that like all the entries are like plus or minus ones. So it's an assumption that like it's flat on its support.
I see, but that doesn't follow just by multiplying by a random sign.
No,
this is an additional assumption.
Sign remains.
Okay.
And even
Okay, sure.
Randomly, so that the signs are random.
Yeah, I mean, the second assumption precludes the first assumption. I mean, in the sense that the second assumption is a stronger assumption than the first one. The first one is irrelevant once we have the second assumption.
Sure, yeah, that's right.
Because if you're assuming that it's a vector of random signs, then the signs are random, which was the assumption number 1.
Sure, yeah. So yeah, I guess I should think of this. You should think of this as an additional assumption that the magnitudes are like uniform and it's M sparse.
Okay.
So the random signs are just like apart from last time, like from the previous assumption.
And Ty,
yeah,
you haven't assumed anything about M, so.
Yeah, so we just want to like analyze this in terms of M.
Okay.
So M is general. It can be 1, it can be N, it can be anything in between.
So not to belabor this point, but I see your diagonal matrix pulling out argument giving you that the signs of the coordinates are random.
Exactly.
But I don't actually see why you will be able to get that the coordinates are plus or minus 1 themselves.
Right. So the uniformity of the magnitude is the second assumption essentially.
Okay, so there's some other argument required, not just this diagonal matrix thingy that you told us, to basically reduce to the case where all the magnitudes are equal or 0.
Exactly. Yeah.
So you're going to do some level set thing so that they're.
Yeah, that's the part that I'm just not going to talk about. So yeah, exactly.
Okay.
Okay, so is the simplified input clear?
We think so.
Okay, so yeah, so I have an m sparse vector and it's all just ones or plus or minus ones. Okay, so now we're just gonna go ahead and like analyze like what we should do for each value of m essentially. So what should we do when m is just equal to 1? So in this case, the algorithm should be pretty clear. And what we want to do is just to add the entries of x. And it's fairly simple to see that if I just add all the entries of x and just take the absolute value, then this will be equal to the L1 norm of this vector itself. So that's just the case of m equals 1. And so that was easy. And so I want to go ahead and make it a little bit more difficult and talk about, yeah.
Sorry, what are we trying to do now? Can you remind us of the goal?
Yeah, sorry, sure. So what I want to do is I want to find a matrix S such that if I have matrix S times this vector and then take the 1 norm of this.
Sorry, so you're trying to find the sketching matrix S such that it preserves the L1 norms.
Exactly, yeah.
Okay.
So you're saying in this m equals 1 case, just so that I understand correctly, choose the row vector 1 1 1 1 1 1 1, and that's all.
Exactly, yes.
Okay. Okay. Thank you.
Okay, yeah. Okay, so yeah, so now just to make things a bit more difficult, I'm going to be looking at m that's slightly larger. So say log n. So among my n coordinates, only log n of them have non-zero entries, and these are all 1 or plus 1 or minus 1. So the idea for this case is that we essentially want to reduce the previous case where m equals 1. And the way that we're going to make that happen is to use hashing. So let me briefly illustrate how this would work.
Okay.
So again, at the top, I have my log n sparse vector of random signs. And at the bottom, I have log n buckets approximately. And what I want to do is I want to go ahead and start just throwing each of these coordinates, each of these n coordinates into a random one of these log n buckets. And when I do this, if I get zeros on my coordinate, then I'm just throwing a 0 in this bucket. And whenever I hit one of these non-zero entries, I actually get something. And because I'm choosing these buckets randomly, with high probability, all of these non-zero entries are going to end up in separate buckets. And at the end of the day, what this means is that each of these buckets essentially looks like this m equals 1 case, but I just have log n of them. And so what I want to do at the end after this hashing process is just to add up all these buckets together. So I add the contents of each bucket. So if I implement this as a sketching matrix S, then what this looks like is this, where I have n columns and log n rows, where the ith column is going to look like, the ith column corresponds to the hashing process of the ith item, and its bucket is going to be one of log n many buckets. And so what I end up is a matrix where each column is a random standard basis vector and log n dimensions. So this is what my hashing matrix looks like. And when I apply this to my sparse vector x, then what I'll get is I'll essentially just be able to condense the matrix where I only keep the non-zero entries, but they lie in separate buckets. And again, in this case, it's pretty easy to see that the L1 norm of the sketch Sx is going to be the same as the L1 norm of x.
So Ty, can I just confirm? So in this case, each row of the sketching matrix would be n over log n sparse?
Correct, yeah.
Okay.
Okay, so is this step clear when our m is at most log n?
Yeah, but yeah, of course, the interesting thing, I mean, this is like you're saying if there's log n entries, I'm going to throw away all the zeros essentially using this idea. But
Yeah.
what is this log square n?
Yeah,
That's
so
what
that's
next, right?
yeah, that's the next step actually. So great point. So yeah, so what if m is log squared n? So if we do the previous approach with only log n hash buckets, then the problem is, of course, that the buckets are going to be crowded. So we're going to have lots of items for every bucket. So how do we avoid this case? So we could just have more buckets, but like that's nothing different than the first case. So what are we going to do here? What we're going to do is sampling. So sampling is going to essentially allow us to take a slightly denser vector and reduce it down to a sparser vector, and then we'll be able to do what we did before.
It won't be one, but like a small number of.
So what we're going to do is we're going to sample each coordinate with probability p, which is 1 over log n, and then scale the entire thing back by 1 over p, also known as log n. And what happens then is, in expectation, after the sampling process, the L1 norm is the same because we're sampling with probability p and then rescaling back up with 1 over p. But the good thing about this is we only have an expectation p times log squared of n, which is just log n non-zero entries. So this is exactly the situation that we want to be in order to apply our earlier results. So in picture, again, we have the slightly denser vector, and then we'll sample each coordinate with probability p and then scale up with 1 over p so that we're left with this sparse vector that's only log n sparse. So any questions?
And so Ty, you couldn't have, I mean, one could have asked the question, why did you not subsample down when the sparsity was log n? But you probably need some Chernoff bound to work, or so you need log n density.
Right, yeah. So the log n, like the intervals of log n that I chose is just I guess kind of convenient to think about like the scale. In general, like one could take this, like you could jump in like intervals of like 2 or 10 or something, but
sorry, that wasn't my question. My question was when the sparsity itself was log n.
Yeah.
Couldn't I have subsampled down to like square root log n?
Sure, yeah, but like at some point, like I need to just choose something large enough so that like I can start like making progress, I guess. So for me, log n is just for the purposes of this discussion, log n is like a convenient like bound that we would want on this problem.
So you're not using the fact that not only is the expected L1 norm the same, but it'll be close with high probability because there's log n expectation to survive. You're Anupam asked, like you're not using a Chernoff bound here because
no, this is only an expectation.
So you're okay with it? Okay.
Yeah, exactly.
So I could have actually sampled, with probability 1 over m, I could have sampled, right?
Yeah, exactly.
And then I could have got a single coordinate out of it, and it has terrible variance, but
yeah, exactly.
So why can't I do that?
why don't I do that?
I'm kind of building up to that discussion, actually.
Okay.
Yeah. So let me just implement what we just said in terms of the sketching matrix. So I have this vector that I want to sketch. I first sample, which goes from n columns down to n over log n rows in expectation. And then I'll rescale and then hash the surviving n over log n entries down to log n buckets. And this will give us a sparser version of the vector, but then scaled by the probability so that it has the same L1 norm and expectation. Real quick, does this still work for the original case of m equals log n? Well, this doesn't work because if I sample like this 1 over log n sampling probability is a bit too aggressive for these like smaller scales. So in general, what I have to do is I have to stack up the previous construction together with this current construction so that this top block just hashes every entry into log n buckets. So this is going to be essentially be for preserving the norm of the sparser levels. And then the second block is going to be for preserving the norm of anything that has sparsity between, say, log n and log squared of n. Okay. And at this point, in general, the construction is going to look like the following, where so if m is in general some like log n to the power, say, I, then I want to sample with probability pi, which is approximately like log n to the -1 plus 1, so that I essentially have about log n entries left. And then I'll just hash the remaining entries into all of log n buckets. So this is the general algorithm. And then what I have to do is like I have to stack all of these levels on top of each other. So so what you said about like just choosing like the sampling rate to be 1/n is essentially what we do. But we have to guess every single level of the sampling level and then just stack all of them up on each other. So that's the construction. So any questions?
Well, so if you don't know what M is beforehand and you stack all of them up together, the right level will preserve the norm. But what about the other levels that weren't the right guess of M? Well, won't they affect the norm? Okay.
Yeah, that's a good question. So we'll get into that as well.
Okay.
Yeah. So yeah, I think you guys are just way ahead of me. But yeah, so in general, like the first level, we'll just hash everything into log n buckets. I'll sample with probability as mentioned before, rescale, and then hash into log n buckets. And I do this all the way until p is like 1/n. So this gives me log n blocks, which corresponds to just guessing log n levels of m. And yeah, so at first glance, the easy analysis to do is to show that this has a distortion of at most O of log n. So why is this the case? So for at every level of sampling and rescaling, we'll basically have a contribution of around the 1 norm of x in expectation. And since I have O of log n blocks, that means that in expectation, like the L1 norm of this thing is at most log n times the 1 norm of x. And then by a Markov bound, like I have this bound in expectation, and so this also holds essentially with constant probability up to constant factors. But yeah, so do we like really need to account for like every single of these contributions for like all log n blocks, since that's what's giving us essentially the log n distortion factor? So in order to remove that, we're going to do a bit more of a careful analysis. So let's consider one of these blocks that sample at a much lower sampling rate. Or sorry, a much higher sampling rate. So relative to m, if our sampling rate is very high, then what's going to happen is that, so if we have only log n buckets, but we sample, say, like, let's say like square root n items, then what's going to happen is that all of these items are going to hash to the same buckets, and then they're going to cancel each other out with the random signs. And I don't want to get into the calculations to make this work, but essentially what this says is that if the sampling rate is too high, then the contribution from this block is going to be a lot smaller relative to the 1 norm of your entire vector. So if you do the analysis, this kind of analysis, you can see that like any block that's lower than like around 1/m is going to contribute like only an epsilon amount of mass. And similarly, when you look at these like lower sampling rates, so suppose that like my m is say like around square root n, but my sampling rate is like all the way at the bottom where I sample with rate 1/n. And in this case, I don't even sample any of my non-zero elements. So in this case, like this also has a contribution of 0, even though it has like a very large contribution in expectation. So if you put these together, what you end up seeing is that only one block whose sampling rate is essentially just right, where it's around 1 over the sparsity, will contribute an expected mass of the 1 norm of x. And this is the idea that's needed to get O of 1 distortion. Yeah, Pravesh, is that a question?
No.
Okay, cool. So any questions up to here? Okay, so yeah, so this was the analysis for the M sketch, which allowed for the O of 1 distortion. And now what we want to do is we want to achieve a 1 plus epsilon distortion.
So
And,
this
yeah.
was O of 1 distortion for a single vector, right?
Exactly, yes. This whole part of the talk is only going to cover the result for embedding one vector.
Okay.
Okay, so yeah, so we'll see how to modify this construction to get 1 plus epsilon distortion. So what was the problem that prevented us from getting 1 plus epsilon versus O of 1 distortion? So if you go back to the slide where we analyzed this M sketch, the problem was that we only had this bound in expectation rather than with high probability. And that's what forced us to use the Markov bound to get an O of 1 distortion. So what we want to do is we want to replace this, expected 1 norm contribution with 1 plus epsilon with high probability instead of in expectation. And this would be possible if only we sampled enough entries, right? So if we expected to sample at least 1 over epsilon squared items, so the expectation can be written as like p times m, where m is the sparsity and p is the sampling probability, then yeah, we just use Chernoff bounds. But the problem is, if we fix these sampling rates P, then this in general doesn't happen. Like whenever we sample with probability P, if we have a vector that's 1 over P sparse, this is not going to give us what we want. So what we need to do here is to avoid this worst case by randomizing P enough. So this is the main idea behind our new technique of randomized sampling rates. So in order to analyze this algorithm, I want to simplify the setting again, where this time I'm just going to say that I just have all ones on its support, since we no longer care about this, these random signs now that we talked about the sign cancellations. So I take my vector to be all ones on M coordinates, and we're going to sample the coordinates of X with probability Pi, which is 1 over B to the I, where B, I need this flexibility to choose B later. Before we chose it to be log n. And then again, we're going to scale it by 1 over Pi. Now, so after sampling and scaling, this is what the picture looks like. And for this vector, we want that with probability at least 99%, I either want to sample none of these entries at all, or I want to sample at least 1 over epsilon squared entries. So this is what's going to, these two cases is what's going to drive our casework on what bound of B we want. So, so let's do some casework on Pi times M. So remember that this is the expected number of entries that we'd sample. So as mentioned earlier, if Pi times M is at most 0.01, then what we have is that we sample none of these entries with probability at least 99%. And this is just by a simple union bound over the M entries that we were supposed to sample. On the other hand, if we can expect to sample at least 1 over epsilon squared many items, then what happens is that the sampled mass concentrates around the expectation up to a 1 plus or minus epsilon factor. And the rescaling doesn't really matter, since everything's just multiplicative. So what we want to do is just avoid this middle white space, right? We just want to randomize enough so that we don't get any of these happening. And in order to analyze this, I first want to, it's going to be convenient to take logs of everything. So I'm going to instead be thinking of myself doing casework on log of Pi times M, and then I just want to avoid the interval log of 0.01 to log of 1 over epsilon squared.
I have a quick question, Ty.
Yeah.
What is the union bound over on the left-hand side?
Yeah, so I have M items.
This is just for one level. You don't get for one. I see. So okay, never mind. So there's only one M you care about here.
Exactly. Yeah.
And you're saying with probability 9. Okay, got it.
Yeah, exactly.
And Ty, what's the subscript I supposed to indicate?
Yeah, so I recall that in the simplified setting, I'm sampling, I have to guess many different levels. So Pi here is 1 over B to the I. So I in general,
B is a constant.
B is going to be some parameter that we choose later. It'll depend on epsilon.
So in your results, I mean, there's no dependence on this I, right?
What do you mean?
Like you're starting off with an M sparse vector, no I.
Yeah.
And the guarantees you want are in terms of either, if you just, so neither of these things has I in it. So how should I think of I as?
Yeah. So essentially, like, if so I can choose B. Okay, I guess this wasn't mentioned clearly, but I can essentially think of just looking at a single level where like this I is close to the appropriate choice of I. So whenever whenever this I is like much different from like whatever choice that would give me Pi is around 1 over M, like it's really like irrelevant by the previous analysis. So essentially, like, unless my I is like just right, I'll either have overcrowded hash buckets and then like random signs cancel each other, or I just won't sample anything. But I'm kind of zooming into like the one that's like close, like the ones that are kind of closer.
So I should just ignore the I and just look at the probability P. And in my mind, I want to think of P as being either like 1 over M or like 1 over epsilon squared times 1 over M, etc.
Yeah, I think that's fine. Okay, so I'll go back to this picture. So I took logs of everything. And now I want to, so we're in the setting where I want to choose Pi randomly in a way that avoids this white space. So I'm gonna give myself a bit more space to analyze this. Recall, yeah, so again, I think I was getting into this next, but I'm choosing my PI to be 1 over b to the I. And then I'm looking at all these different sampling levels, right? So if I draw this on this line, then if I look at the log expected number of entries sampled, then these are going to appear as these like regularly spaced points on this line. And the distance between each of these points is going to be log b, which is like the factor of change. And now I want to avoid this bad level, which goes right in this like bad interval, right? Now, my idea is I want to think that this white space is small enough relative to this like log b, so that if I shift this entire picture by a uniformly random number between 0 and log b, then like I'll be able to avoid this bad level with high probability or an expectation. It turns out that expectation is going to be what I want to see. So what do I do? Suppose that I choose b such that the length of this interval is going to be only an epsilon over 100 fraction of log b. So if that happens, so if I choose my b in this way, and furthermore, I consider like randomly shifting this entire picture by like a random number between 0 and log b, then what I have is that the probability that any one of these i's lands in this bad level is going to be at most epsilon over 100. Since I'm shifting by like log b, but the bad interval is only of size epsilon over 100 of that. So that's how I want to choose my b. And so if you back solve what b should be, you'll see that b should be around a singly exponential and 1 over epsilon. So that's just doing the math out here. So that's the choice of b I want. And so yeah, this is the entire idea. And in turn, what happens is since I land in this bad level only an epsilon over 100 fraction of the time, in expectation, like any one of these bad levels will contribute only like up to like an epsilon over 100 fraction of of its mass. And that's what's going to allow us to get the 1 plus epsilon distortion. So any questions about this picture? It has a lot of stuff on it, so I want to make sure it's clear.
Sorry, could you give intuition on why b needs to be exponential in 1 over epsilon rather than polynomial?
Yeah. So here, like I need my interval, which is of size like, so the interval goes from log of 0.01 to log of 1 over epsilon squared, right? So the length of this interval is like about like log of 1 over epsilon squared. And this I want to be an epsilon fraction of log b, right? So that tells me that like log b is like 1 over epsilon, and therefore like, yeah, b is like exponential 1 over epsilon.
Got it, thanks.
Yeah. Okay, so just to finish up this this proof, so if I take b to be as mentioned before, then what I want to do is I want to choose a random tilde b, which is going to be my shift, which I set to be b to the power u for some uniformly random u between 0 and 1. And this just corresponds to what I said earlier about the randomly shifting the picture. And then what happens is like we want to sample at rates pi, which is tilde b over b to the I. This change in sampling rate is going to change a number of the other parameters in this construction. But one can show that if you do the calculations out and choose the appropriate parameters, this works. So in conclusion, so what we've done is we have proven exponentially improved bounds in D and 1 over epsilon for dimension reduction in L1. And the dependence D here is tight up to polynomial factors in the exponent. And in order to get these results, we introduced 2 new techniques. One is the randomized sampling rates, which essentially is a classical streaming technique, but we put a modern twist on it. And our other technique is avoiding a net argument through the use of L1 leverage scores. So that's all I have for today. Thank you for listening.